Okay, we're going to continue on here, chapter 12, and we were talking about in chapter 12, equilibrium. Remember that equilibrium really involves a certain type of reaction, which, as we talked about, is a reversible reaction, where we do have basically arrows heading in both directions. And as we talked about, there's really a forward direction as it goes from reactants to products. There's also at some point the products will come back together and head back in the opposite direction, which is known as the reverse direction. And remember that as we talked about, when it does reach chemical equilibrium, again, it doesn't mean that you have the same amount of everybody on each side of the arrows or anything like that. It is referring really to the rate. And what it means when it does reach that chemical equilibrium is the rate of the forward reaction will eventually equal the rate of the reverse reaction. So what that essentially means is once that is reached, everybody in terms of their concentration, everybody in terms of their pressures, and maybe you're dealing with gases, will basically maintain their concentrations or pressures because essentially as quick as it goes this way, it's going to come back the other way just as quick. And what that will essentially do, like I said, is basically lock everybody into place in terms of where they're at. Um, we can write an equilibrium expression, which is what's referred to as K. And K is essentially a lot of times really just the products over the reactants. And a lot of times we will calculate the concentration of our products over the concentration of our reactants. And that's what's sometimes referred to as Kc for concentration. We do, when we write that, take into account the coefficients that we find in the balanced equation, and they do become the exponents. So in this example here, we take c to the c, d to the d divided by a to the a, and b to the b. Now, what is K? K is, again, the ratio of products to reactants. And as we talked about last time, it is specific for how the reaction is written. It is also specific for the temperature. So as we delved into a little bit last time, the temperature is really the only thing that will affect the actual value of the equilibrium constant. And again, what we were talking about is if you were comparing, for example, the equilibrium constant at, say, 25 degrees Celsius to the equilibrium constant, say, at 50 degrees Celsius for the same reaction, those values would be different. But again, as we also talked about, you could run a bunch of different experiments all at 25 degrees Celsius. You could start with all reactants, all products, a little bit of everybody thrown in the mix, and you will always end up with the same ratio of products to reactants at that particular temperature. So as long as you don't change the temperature, you would expect the same equilibrium constant value because it is a constant value at that particular temperature. And again, that's something a lot of people have a hard time with. They think, like, I started with more in this reaction or less in this reaction, so I should get a different value of K, but it will come out the same. We could also, if we do have some type of pressures involved or gases involved, we could also write what is sometimes referred to as the Kp value, which is done the same way. It's the partial pressures of our products divided by the partial pressures here of our reactants. And in most cases, it can happen, but in most cases, the value of Kc and the value of Kp are usually not numerically the same, but it can actually happen that they are, but usually they're not. But when we also talked about is these values of K does tell us a couple of things. If we have a large value of K, what that means is when we do reach equilibrium, we should expect mainly products to be present. So we should kind of expect our products to be there. Again, a large number on top divided by a smaller number on the bottom is going to yield us a larger number overall. And if we have a small value of K, it means that when we do reach equilibrium, we would actually expect to mainly have reactants. And same math idea, if you had a smaller number on top divided by a larger number on the bottom, you would get a smaller number overall for your value of K. Now, we can, if we needed to, go from KC to KP. And we also talked about the idea, a couple things more about K. Again, it is just a number, so there's no units associated with it. But we can go from KC to KP by using that equation that we saw, which was something like the KP is equal to the KC RT delta N. Remember that this is our gas constant, and that is 0.08206. This is our temperature in Kelvin. And as we talked about last time, I think we had an example as well. It's always important to do the moles of our products minus the moles of our reactants. And that is because mathematically speaking, as we talked about last time, if you do end up with a negative value there for delta N, it is going to mathematically be different than if you had a positive value. So sometimes people, again, just take the difference and they kind of ignore the negative if it's there. And you do not want to do that. This would be in a formula here that we would use, obviously, if perhaps we were looking for, say, Kc, and the only thing that we were given is from pressure, so we could only calculate Kp perhaps, and vice versa. Maybe we were given concentrations and we could calculate Kc, but we also maybe want to know for some reason the Kp value. So that's the one that we use to kind of go between the two. Any questions on any of that stuff there that we talked about last time? Okay. All right. So I think we ended on an example. So I think we're about here, and we sort of talked about this, but this will be good finishing review here. We talked about homogeneous equilibrium last time, but also there's heterogeneous equilibrium. And heterogeneous equilibrium, like a heterogeneous mixture, means you see things in different phases. So your reactants, your products will be in different phases. So in this example here, we got some solids and we also have some gases here. Once again, as we talked about previously, the solids are pretty much just going to kind of sit there, really not participate too much in equilibrium or anything like that. So we don't include it in the equilibrium expression. So they're basically held constant, which means really I'll scratch this out, the proper Kc expression here for this reaction would be basically just our product there, which is our CO2, as our other product is a solid and our reactant is also a solid. And we could write our Kp value here, which would be the partial pressure here of CO2 as well. I think we also talked about the idea that if you had solids or liquids there on the product side and just some stuff on the reactant side, you had to write an equilibrium expression 1 over the reactants, right, is how you would sort of do that. So ultimately, that brings us back to something we really did sort of touch upon last time as well, which is pretty much when you're writing K expressions, what should go in is anything that's in the aqueous phase or anything that is in the gas phase. And those are two things that are pretty much moving around and ready to go to react, right? So they have a pretty big effect on equilibrium. As we talked about, gas molecules are flying around with lots of energy, which means they're good to go. And aqueous guys are typically ions that are floating around in the solution, no bonds to break. They're ready to sort of start reacting and stuff like that. Things that do not go in are pretty much your other two guys, as we've been talking about here, solids and liquids. So those two things are not included into the equilibrium. Typically, most concentrations of pure liquids remain relatively constant throughout, like water is a very common one. And as I mentioned before, solids pretty much are just going to be sitting there. Really, the only way that they can sort of participate, for example, in a solution is they would have to dissolve. And at that point, they're no longer solids. They would be aqueous ions, and you would include them. So in the solid state, it's just going to kind of sit there and really not be included. Any questions on that there? All right, that's what we kind of see here. Again, solid guys just kind of sitting there. And it's really those sort of active gas molecules as they are moving around. And as I mentioned before, typically speaking, our Kp in this case would be our CO2, which is really the only sort of active sort of process in this. All right, so I want to try one more here. Consider the following. The partial pressures of each gas is 0.265. Calculate the Kp and Kc for this guy at 295. So take a few moments and come up with both the Kc and Kp value here. Okay, let's take a look and see. So once again, we want to sort of analyze maybe what would be the best one to solve for here. And since I see pressures, I'm going to hopefully assume that you went with Kp first, since that would make the most sense. Remember, regardless of what equilibrium constant it is still really all the same. It's the products over reactants. So that's where we want to start here. So our Kp in this case would be our products. So the partial pressure there of NH3 times the partial pressure of H2S. Once again, the coefficients here are 1, so we don't have to put anything there. Here we do have a solid for our reactants, which means we are not going to include it in our equilibrium expression. So that is it. And since each of our gases is 0.265, we're basically just going to kind of square basically 0.265. And it's going to be 0.265 times 0.265. And we will end up with a Kp of here 7.02 times 10 to the minus 2 in this particular case. Any questions on that so far? Now that we have the Kp, we could use our formula there to, again, sort of cross over from our Kp to our Kc value. And once again, I believe it is this formula. We'll go with it. Why not? RT delta N. So we need a couple of things here. Our temperature is already in Kelvin, so that's good to go the way it is. We do want to calculate our delta N, and as the question was asked there, it is actually the moles of gas molecules on each side. So those are the only ones that you should count, anybody that has a G. And once again, the easiest thing to do is just take the coefficients of what you see there. So on our product side, minus our reactants here, we would have 2 minus 0, which means our N in this case would equal 2. At that point, I think we have everything. Remember, like normal, you always have R. And again, you can use the rounded version there of 0.0821 if you like. But again, I typically use this number. That means in this case, we got a 7.02 times 10 to the minus 2 is equal to Kc. We're going to go 0.08206. We're going to times that by our temperature of 295, and we're going to square it. Once again, here, I'm going to take care of what's in the parentheses there. So we're going to go 0.0206 times 295, hit equals, and then square it. That would be good. That's going to give me something like 7.02 times 10 to the minus 2 equals Kc. And I got something like 586.012739 if I don't take out any numbers. To solve for this, we're going to divide this right to the other side there. And that will get us here. 2 to the minus 2 divided by that there. Probably hit the right button. Would go good. Try that. All right. And that's going to get us here a Kc value of, we'll call it 1.20 times 10. Zeros 1, 2, 3, 4, I think, if I'm not mistaken. There we go. Any questions on that? Yeah. Yeah, so it is, again, it's the moles of just the gas molecules. So since really sometimes people go on autopilot on that and they just, add up what's on each side, you do want to make sure you take a look at it. Since that is a solid, we would not include it. Yeah. Other questions? Once again, here we see kind of what we talked about, our Kp and Kc value, not really the same numerical value, but they both tell us the same thing. And what do they both tell us? Is this a large or small value? It's small, which means at equilibrium, we should mainly expect reactants being present in this case. Yeah. Any questions on that there? Questions on calculating Kp, Kc, one from the other? Right. Obviously, I think we talked about it last time, but again, always good to reiterate. If you are calculating anything that's a equilibrium constant value, they do have to be equilibrium concentrations or equilibrium pressures to go in there. We will talk about when they are not, what we have to do. All right, let's talk a little bit about ways that we manipulate certain equations. So for example, if we have these two equations, There may come a time where you may have to sort of move around certain equations that have equilibrium constant values associated with them. As we mentioned before, when you actually do see a value for K, it is specific for exactly how that reaction is written, and it is specific for that temperature. So we have the first one up here, which is A plus B goes to C plus D. We could write the equilibrium expression, which looks like this. And if we have the second reaction there, which is C plus D goes to E plus F, that would be our equilibrium expression there of our products over reactants. One thing that you may be familiar with is if you are adding equations together, maybe we did it in redox, I guess. You don't really do too much Hess's law. We'll do that here. But you can cancel out anything that's on opposite sides of the arrows and opposite equations. Kind of treat the arrows like an equal sign, like, kind of subtracting it away. So if we were to add these two reactions together, everything that's the same on opposite sides of the arrow will either completely cancel out or can be reduced down if they don't completely cancel out. And this will give us our overall reaction here, which is A plus B goes to E plus F. And if we write the equilibrium expression for this, that is it right there. So how do we get to this equilibrium expression from these two individual sort of reactions? Basically, if you multiply both of those K values together, C and D cancel, right? And we're left with EF over A and B. So one way that you might have to look at something or try to determine the equilibrium constant value for a particular reaction is by adding some different reactions together. And that is because, as you may know, not all reactions occur in like a one-step sort of process. Again, some occur in multiple step type processes here. So one thing that we do with equilibrium constants is, and this is something, frankly, people screw up most of the time on because they want to add. So we do not add K values. We actually multiply K values. So if you're taking two reactions together, two equations together, 3, 4, however many you got, and you need the K value from putting all those reactions together, you multiply the K values together to get the one that is written there, like we see here. Any questions on that there? Some other common things that you might need to do is, for example, maybe you need to reverse a particular reaction. So maybe you have this reaction here. This is the K value specific for the way that reaction is written. But maybe you need NO2 on the reactant side and you need N2O4 on the product side. So basically we reverse the reaction here. So as we go from here to here, we did a little reverse of the reaction. And what that does for the equilibrium constant is our reactants become our products become our reactants. So we actually will take 1 over the equilibrium constant value. So if you need to reverse a reaction, you actually take 1 over the K value to do so. Another very common mistake people do with that is they just change the sign, and you don't do that for this. So again, with K values, if you reverse the reaction and you need the K value for the one that you just reversed, and you take 1 over the K value, will get you there. And the other thing that's important is if you are writing this equation here, the proper K value would be 216. If you're writing this reaction here where N2O4 is the reactant, this would be the proper value for K. So as I mentioned before, when you see a K value for a reaction, how it's written at that particular temperature, they're kind of locked together. So if you do something to that equation, like reverse it, you have to adjust the K value, or if you take it and add it to something else. Any questions on that there? So what are some other things that you might do? Well, some other common things that you might have to do along the way is, let's just say we have A plus B goes to C plus D, and we have a K value here for that. And let's just say that we did not need 1 of A, but maybe we needed 2 of A. So if we had to go through and multiply this equation by a constant number of 2, what does that do to the equilibrium expression? So let's take a look and see. The K here obviously would be like what we had on the previous page. Looks something like this. And the K value for this guy would look something like this. What is the difference as I go from there to there? It is squared. Yeah, so it is squared. Very common mistake people will do, multiply by 2 instead of actually squaring it. So it's actually the square of it. By the way, if I multiply by 3, what would it be? Be the cube of it. Multiply by 4, take the fourth power of it, right? So if you have to multiply the equation by a common number, you basically take the K value to that common number. So if you kind of multiply, you take the K value to the number basically that you multiplied it by. What's the last thing that you might have to do is, let's just say we started with the second equation there, and we wanted the first equation going this way, right? So basically what I did here is I divided everybody by 2, right? If I'm going kind of backwards, right? Starting with the second equation, going to the first equation, which means what is the difference as you go from this K expression to that K expression? It is the square root, right? And that's because I divided by 2. If I divided by 3, I would take the cubed root. Yes, divided by 4, take the fourth root. So if you have to divide, you actually take the root to whatever you divided by. So if you divide by a common number, you take the root of that basically on your calculator. So those are probably 4 very common sort of manipulations of equations that have K values associated with it, and 4 very common things that people screw up on a lot of times. Yeah. And again, I tell you again, the mistakes that people make when adding them together, equations, they add the K values instead of multiply. When they reverse the reaction, instead of taking 1 over K, they do the negative, which they should not do. And on this one here, they multiply by the number or divide by the number when they should be kind of taking it to that power or taking it to the root of that. So those are very common errors that people make. Why would you need to do this? Like I said before, maybe you're given a set of individual equations where they all have K values and they're like, hey, use those guys to figure out what the K value is for this equation. And you got to kind of move things around and keep track of what you did and see what the adjusted K value would be. Any questions on that there? So let's try one. I'm looking for what is the K value of this guy based on these guys' equations. So take a moment, see how you have to manipulate those equations and what you should end up with for the K value here. Okay, so let's take a look. So if you're not familiar how to do these, maybe you've done Hess's law in your past chemistry class or something like that. But the thing to do here is really not overcomplicate it. Yeah, keep it simple, which basically means you just want to get everybody to the correct side and just to make sure you have the right amount of everybody. So for example, I'm going to look at the first equation here, and I see A and B on the left here in the first equation, but in the one that we want to make, it's on the right-hand side, and that means I do need to reverse that first reaction or equation. I do need 1A and 1B, so I don't need to do anything else other than really reverse the first one. So I'm just going to rewrite the first equation there in the reverse direction, which will put my A and B on the correct side. And now because I reversed it, what do I do with the K value? I should take 1 over the K value in this case, right? So I should take 1 over 100 would be what I should have because I reversed it. All right, so I got my A and B over there. I clearly can see E and F is on the left-hand side in the equation I need. It's on the right-hand side there on the equation that I have, which is here, right? So I do know I need to also reverse that one, but I also see that I need how many E's and F's? I need 2, but I only have 1, which means I also need to multiply that equation by 2. So I'm going to reverse the bottom equation first, which means it will look something like this, right? Which means my K value, just like the first one, should then be 1 over 20 basically here. But I also need to multiply this by 2, which means I'm going to do that as well. do that in orange. Why not? We're going to multiply this entire thing by 2, which means I'm going to end up with, I'm going to erase it at the end here, 2E, 2F, 2C, and 2D, which means because I multiplied by a common number, I then need to take the K value to that common number. So I'm just going to get rid of the kind of parentheses here. And I basically multiplied everybody by 2. Any questions on that there? Now, if I did this correctly, since I'm out of equations, I hope I did. Otherwise, I'm in trouble here. When I add these together, I should be left with the equation I'm looking for. So I do have 2C on the left. That should cancel out the 2C on the right. I have 2D on the left. It should cancel out the 2D on the right. And at this point, if there's nothing else that cancels out, kind of like if you remember redox, everything on the left-hand side of the arrow stays on the left, and everybody on the right-hand side stays on the right-hand side of the arrow. And you'll end up with 2E plus 2F, which is on the left-hand side of the arrow, a little A plus B action, which is good. Any questions on that so far? So if I call this K1 and K2 in this case, the K value for this reaction, which I'm looking for, can be found by doing what? We're going to multiply K1 times K2 in this case, right? We just have to keep track of everything that we did, which we did. So if I do that, that's basically 1 divided by 100. Which means I got something like 0.01 here. And that is 1 divided by 20. And then I also need to do a little squaring of that. And that's going to give me here 0.0025 when I do that. Now I could take those numbers and multiply them together. So my, I'll go over here actually. My K will equal 0.01 times 0.0025. And that will get me, we'll go with, I'll do a little scientific notation here, 2.5 times 10 to the 1, 2, 3, 4, 5 minus 5, looks like, by counting my zeros right there. Any questions on that? Yeah.
Still not clear why we took the top reaction.
We flipped the top, this one here. Yeah, we flipped it because in the equation that we're looking to basically build, so you're basically trying to build that equation in the circle there. The simplest answer is I see A and B on the left, but it needs to end up on the right, which means you got to flip it around. And that's really the easiest way to approach these things. Sometimes people make it way more complicated than it has to be. It's really just think about it very simply of, I need to get these guys to that side, or I got to move these guys to that side, and how many of those things that I need. Usually everything else that you don't really need for the equation that you're looking for, if you kind of move everybody to the correct side and have the right amount of everybody else really should properly cancel out and kind of get out of the way of what you don't need. Other questions on that? All right, let's try another one maybe. What is the K for the bottom equation here? Again, working off the top 2 equations. So we're looking for this equation based off of those 2. So see what you come up with. So once again here, I'm not going to overcomplicate it. Just going to simply just get everybody on the correct sides and make sure I have the right amount of everybody. So with that being said, really the only equation that has N2 in it is the first one. And when I look at the equation I'm trying to build, I got N2 on the left-hand side, which it is, so that's good. Do I have enough of the N2s? I don't. I have a half, but I need 2. That means I do need to multiply the top equation by, I'm going to go with 4 in this case to get me to 2, I hope. So I'm going to take this top equation here, and I do need to multiply it by 4. And when I do that, I'm going to rewrite it underneath this equation I'm looking for. 4 over 2 is 2N2. 4 times 3 is 12, divided by 2 is 6H2. When you multiply that 4 to everybody. And that gives me 4 times 1, which is 4. That means that my K1 here is 411. Since I multiply by 4, what should I do with that K value? Should take it to the 4th power. Remember, whatever you multiply by, you're going to take it to the 4th power. Not bad so far, I think. All right, so I'm gonna do the same thing here. I got water, which is my other reactant that I'm shooting for. And again, the only equation really that has water in it is this one. And since I already did something with the first one, I'm probably not going back to that one. So this water's on the left-hand side, which is the correct side for what we need. So we don't have to do any reversing in this case. But again, when I'm all said and done, I need 6 waters and I only have 2, which means I got to do a little multiplying by 3 in this case, right, to get me the proper number. Again, we're going to multiply everybody in that equation by 3, not just the one that we need. That's going to give me 6 waters. Goes to here 6H2 plus 3O2. My K2 in this case 0.345. Much like the first one here, I multiplied by 3, right? Not 6, by the way. I multiplied by 3, and that means I also need to cube this guy. I am once again out of equations, which means I should have hopefully did this correct. And let's see. We're going to add these together. And once again, anything that's on opposite sides can cancel out or reduce. We have 6 H2s on the left and 6 on the right. And I think that is it. Everybody on the left-hand side stays there. So 2N2 plus 6 waters goes to 4 NH3s plus 3 O2s. Doesn't really matter which order you write it, but everybody's on the correct side with the right amount. And we did get the equation that we're looking for. So in this case, we didn't have to do any reversing, but we did have to do some multiplying, right? So again, we want to keep track of what we have to do. Any questions on that so far? Obviously, to calculate our K, just like last time, since we added these together, we're going to multiply our K values in this case. So I'll go up here on top. So our K in this case would equal basically 411 to the 4th times 0.345 to the 3rd power. And if you do all that good stuff there, I'm assuming a big number based on my made up numbers I used, times maybe something like 1.17 times 10 to the 9 in this case, yeah. Any questions on that one? Yeah. Yeah, so you mean when we multiply by a common number, why we kind of use powers instead of multiplying by? Yeah, so the simple example would be just looking at just this one that we looked at previously. So when we do something like this, again, our K is C, D, A, and B. Now let's just say we multiplied this guy. Basically, we'll do 3 like we kind of did in the example. This would give us 3A plus 3B goes to 3C plus 3D. When we write the equilibrium expression for this, it would be C to the cubed, D to the 3 there, A to the 3, and B to the 3. So actually, when we multiply by a common number, the difference between these two things is basically this cubed because we multiplied by 3. We multiply by 2, it would be squared because the coefficients would then be 2's in that case, basically the difference between them. And it's basically like squaring it. And if we multiply by 4 like we did in the first one, the difference between the original and that one is basically to the 4th power. So that's a very, very common mistake that people make is when they multiply like that, they'll just multiply the K values. Same thing with dividing. We take the root of that we divide by. We don't want to just divide the K value or anything like that. So if you remember anything like Hess's law or manipulating enthalpy values, it is different than how you play with those things based on the relationship that we have here. Other questions on that? Okay. So again, you may have to manipulate equations. And those are the things that you want to sort of think about. So summary of some of the stuff that we've been talking about here with equilibrium expressions. Once again, equilibrium concentrations is usually molarity. I think I mentioned it the other day, but definitely usually atmospheres is the unit that you want to be kind of using when you go into sort of equilibrium sort of problems if you're dealing with some type of pressures. Once again, we leave out solids and liquids. We include aqueous and gases. No units for your K value. And as we've been talking about, when we do see a K value, it is specific for exactly how that thing's written at that exact temperature. And then obviously, as we've just been doing there, if you have to do some type of manipulation of an equation that has a K value and you need to add a couple equations together, we multiply, as we just talked about there, if we multiply a equation by a common number, we take it to that power, we divide by a common number, we take the root of that. And again, if we need to reverse the reaction, it is 1 over the K value. Don't just change the sign. Any questions on any of that there? Okay. All right. And this is what we talked about as well. Again, remember that as we talked about, there's many equilibrium positions. And that's basically referring to the idea, as we talked about, that you can start with different amounts of reactants, different amounts of products. As long as you don't change the temperature, you will get the same ratio of products to reactants. And that was what we were talking about the other day when I did, like, I think 4 divided by 2 gives you 2, right? 2 divided by 1 gives you 2. 8 divided by 4 gives you 2. They all give you the same ratio, basically, even though they're different numbers and stuff like that. So it's the same idea with the equilibrium constant. You get the same ratio at the end, even though you have different numbers. The ratio of those products to the reactants will end up the same. Any questions on that there? All right, then let's talk about a different letter for once. Not very long, but we'll talk about a different letter. And that's the letter Q. And Q is what is referred to as the reaction quotient. And the reaction quotient, which is Q, is essentially calculated the exact same way as you calculate K. So it is products over reactants. So just like you would write the K expression, you would do the Q expression the exact same way, products over reactants. Just like in K, you do take the coefficients as those exponents. You do exactly the same thing as K, except that you use the letter Q in this case. So why do we use the letter Q? There's really 2 reasons why we use Q and a couple different places where they will show up where you would need to use Q. But Q is essentially used in a lot of cases to determine whether or not you're at equilibrium. So maybe you're given concentrations of everybody and you don't know if you're at equilibrium. And you could calculate Q to determine whether or not you're at equilibrium, or you're given initial concentrations of everybody. And you could calculate Q to determine which way you need to go to reach equilibrium. So a basic Q type problem is this. If you calculate Q and you're not at equilibrium, it will also tell you which way you need to go to reach equilibrium. Do you need to make more products to get there? Do you need to make more reactants to reach equilibrium? So that is really the value of Q. We will see Q coming up a little bit later on when we do real equilibrium calculations. There's another situation where you might want to calculate Q. So what do you do with Q? Well, you compare Q to K. And if Q is larger than K, that means that you are not at equilibrium. And in order to reach equilibrium, you need to make more reactants. If you calculate Q and it does equal the K value, then your process is at equilibrium. And you probably won't want to do much with it at that point. It's at equilibrium. And if you calculate Q and it is less than K, you are not at equilibrium, but in order to reach equilibrium, you would need to make more products. So if you want to line it up like this, it's opposite of where it's pointing. What I mean by that, if you just think about a reaction, that's reactants to products. And if you line up Q on the left there and K on the right, it's always opposite of where that greater or equal sign is pointing. So if you have Q is less than K, it's got to go to the left, and on the left on an equation is reactants. So you're going to need more reactants. If you have Q is less than K, it needs to go opposite of that to the right, and you have more products that need to be made. So if you want to do it that way, you can. If you want to put K on the left and Q on the right, then it's the way it's pointing. Whichever way you want to do it, it don't matter if you want to remember it that way. So we do use Q in 2 separate situations, like I mentioned, sort of a straight up Q type question where that's the question that's being asked. You'll be asked like, under this situation, are we at equilibrium or not, and which way we need to go, and we will see it again later on. Now, because Q is calculated the exact same way that you calculate the equilibrium constant, again with the coefficients being those exponents, you could only calculate Q if you are given everybody's concentration, right? So if you're not given everybody's concentration, there's no way to calculate Q. So that's also later on in this chapter how you determine should you calculate Q or not. In certain situations, you don't have enough information to calculate Q. In other situations, you do have enough information to calculate Q, and it can affect your calculation later on in the chapter. And we'll talk about it obviously when we get there, but a straight up sort of Q question is pretty much that question. Are you at equilibrium? And if not, which way you need to go to reach equilibrium? So let's try a straight up question like that. If we started a reaction with 0.249 moles of N2, 3.21 times 10 to the minus 2 moles of H2, and some NH3 in a 3.5 liter vessel, if the Kc is 1.2, first question is it at equilibrium? And if it's not, which way you need to go to reach equilibrium? So take a few moments there and calculate. I would say Q would be good in this case. Again, calculated the exact same way as you would do K. Okay, let's take a look and see. So in this case, we want to know, is the system at equilibrium? That's a big hint. That's a Q type question. So we're going to calculate Q. Again, it is calculated the exact same as you do K. So we're going to take our products over our reactants here. So we're going to go Q in this case will equal the concentration of NH3. And just like we do with K, we do have to square it because of the coefficient that's there. We're going to divide that by the concentration of N2. Again, the coefficient there is 1. And we're going to also divide that by H2, which we do need to take to the third power there, as the coefficient there is 3. So again, the Q expression, exact same thing as the K expression there. We are able to calculate Q in this case because we are not given really the concentrations of everybody, but we can get to the concentrations of everybody. So we have the moles and we have the liters, which is molarity, right? Moles per liter. So that might be the first thing that we want to calculate is the molarity of everybody. So the concentration here of N2 would be our moles of N2, which is 0.249 moles, divided by our liters, which is 3.5 liters. We'll do the same thing for our H2, which is 3.21 times 10 to the minus 2 moles over 3.5 liters. And lastly, we'll do the same thing here for our NH3, which is, in this case, 6.42 times 10 to the minus 2 moles, or to the minus 4 moles, divided by 3.5 liters. So all we're doing here is calculating molarity of each of those, because when we do go into our Q expression, just like when we go into our K expression, if we're dealing with concentrations, it does need to be in molarity here. So we will do that 0.249 divided by 3.5. That's going to give us something like 0.0, I'll call it 711, right? 3.21, make sure you use your exponent button, to the minus 2, divided by 3.5. We got 0.00917. And lastly here, 6.42 to the minus 4 divided by 3.5, going to give us 0.000183 molar. Any questions on that so far? So frankly, now that we have everything, we just need to put it in, right? So we're going to put all those numbers in the right location here. So our NH3 is 0.000183. We want to make sure we are squaring it because of the coefficient. We're going to divide it by N2, 0.0711, and our 0.00917. Once again, we also need to make sure that we cube that one as well. So we pop all that into our calculators carefully here. 0.000183 squared divided by 0.0711 divided by 0.00917 to the third here. That is looking like we're going to end up with a Q value of 0.61. Give or take there. 611 if we want to go one more here. Any questions on that there? So what do we do with that Q value? We're going to take the Q value we just calculated and we're going to compare it to the K value. Is it the same? It is not, which means the first question answered is, am I at equilibrium? I am not, because they don't equal each other. So remember, you'd be at equilibrium if the K and the Q equal each other, so they don't. So that's the first answer, which is no, we're not at equilibrium. Q is actually in this case less than the K value, right? Which tells us for sure we're not at equilibrium. But it also tells us, do I need more reactants or products to reach equilibrium? I do need more products. Again, opposite of where it's pointing towards the product side. I need more products in this case. So this is, like I said before, sort of a straight up Q type question. Are you at equilibrium? And if not, which way you need to go to reach equilibrium? Any questions on any of that there? Okay, so let us then here talk about the calculation of the season here for this class. Yeah, so we're going to talk about how to do really equilibrium calculations here. So let's talk about that. So when we're solving equilibrium constant problems, there's a couple of things that we do. And frankly, we use, or I'm going to teach you, I suppose. We use what we like to call ice tables. And maybe you've used ice tables before. If you took me, you used it in 200A. So we're going to use basically the same thing here in 200B. If you didn't, then maybe it's new to you. It's not too difficult here, but the idea here is we use what is referred to as ice tables. And I stands for initial, change, and 200A we called it end, but here we call it equilibrium. So we use an ice table to help us figure out what is the equilibrium concentrations of everybody if we are only given initial concentrations. So if we're only given initial concentrations, we set up an ice table. So how do we set up an ice table? Well, let's just say we have this reaction here, 2A plus B goes to 2C or something like that. And let's just say that initially we had an initial concentration of A of 2 molar and an initial concentration of B. We'll go with 4 molar. And we want to know what is the equilibrium concentrations of everybody once we reach equilibrium. So, couple of things here. We would start our ice table by using the balance equation there. We would have an I line, which is our initial, which in my made up example here would be 2 molar, 4 molar. Now, there is nothing given to me about C at all in this case, right? So in this situation, it is safe to assume that you got nothing much going on over there. So you have 0 initially of your product. If you did have something of your product, it would tell you. You got so much of that product basically there. So the next part is really one of the most important parts of an ice table, and that is the change. Now, in this particular case, since we are not given anything about the product, and we have no product to start with, this reaction should probably be heading in which direction? The forward direction or the reverse direction? It should be heading in the forward direction, since that's all you got is reactants, right? So that's the only direction that could basically occur. So that means that as this reaction starts, the amount of my reactants should they end up being more or less than what I started with? I thought I heard some whispering of less, and that would be right. So we have the forward direction happening, like we talked about. You need the reactants to come together, right, to make products, right? Which means the amount of reactants should come down, the amount of products should go up. And this is represented in an ice table with minuses and pluses. So our reactants should be represented with minuses, and our products should be represented with pluses. We represent the change usually with the fancy letter of X, because it's like, I don't know what that is. So we use X to represent the change. So when we get to the change part, this would be minus 2x, this would be minus x, and this would be plus 2x. Now, a couple of things. I threw some numbers in there. Those numbers come from the coefficients. Yeah. And if you took me, you know the reason you put those numbers in is because that is your stoichiometry. That is your mole to mole relationship, which you could have used to do like limiting reagent type problems if you were taught that way. Most people aren't taught that way, but if you were taught that way, you could have done that. And if you do not put those coefficients, you will have the wrong mole to mole stoichiometry relationship there, and you will get the wrong answer. So you have to include the coefficients from the balanced equation. That takes care of all the mole to mole relationship, all wrapped up in one calculation without doing a separate sort of calculation. It's all sort of done for you. So very important to take those coefficients into account. Any questions on that there? So what we're going to do then is we're going to carry down on our equilibrium line everything that is there. So this would be 2 minus 2x. This would be 4 minus x. And this would be 2x. At this point, if I wrote a better problem, you would also be given probably the equilibrium constant, for example. Say the k value is 50 or something. We could write our equilibrium expression in this case by doing the same thing as normal. K would equal, in this case, c squared divided by a squared over b, and that would equal 50 in this case, and my made up number, obviously. The goal here is to really figure out what the change is, which is x. And that means at this point, what you would do is you would take the equilibrium line, these guys, and you would stick it into this expression right here. So if we were going to do this crazy one, which we're not going to finish really, because it's crazy enough, you would put in here 2x squared divided by 2 minus 2 x squared times 4 minus x would equal 50. And at this point, you would do some fun math. I don't know how fun that will be, but you do some fun math there. And basically, we would solve for x. And we'll talk about several different ways that you could solve for x and several different things that you could do to actually solve these problems. Again, we're not going to solve this because I clearly just made up some numbers, so I don't want to sit all day doing math here. But the idea is you will solve this through math and you will get x. So what is x really important for? Once you solve for x, that x value that you get there will be the x value you see in the table here on the equilibrium line. So that will be this x value, that will be this x value, and that will be that x value right there. What that's going to allow you to do at this point is actually get a value, a number for the equilibrium concentrations in my example here of A, B, and C. Any questions on that there? Now, how do we do this mathematically? Let's talk a little bit about some math that we might use, yeah? Well, one very popular math thing that we do come across a lot is the quadratic. Yes, quadratic formula, yeah. I vaguely remember that, but that has something to do with this, I think. So one way that we solve it, for example, is x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a, and that is based off of a formula that looks something like this: ax squared, right, plus bx plus c is equal to 0, right? When you use the quadratic formula like so, how many values of x do you get? You do get 2. And we'll talk about one of those values that you get will not make sense, which means when you put it back into that equilibrium line, you will get a negative concentration, which you cannot have. And one value will make sense. Now, just so you know, when you do use the quadratic formula, you can get two positive numbers, you get two negative numbers, you get a positive and a negative number. But the goal is when you put it back into that equilibrium line, one of them, again, will not make sense. It will lead you to a negative concentration. You could do this ice table. And when you do ice table, if you remember, I mentioned units. If you're doing it with concentrations, they should be molarity when they go into the ice table. You can actually do an ice table with pressures, and a Kp value works the exact same way. The only difference is you're using pressures rather than concentrations. And this is the case where I was talking about earlier. It needs to be atmospheres when it goes into the ice table. Even if they give it to you in some other pressure unit and they want the answer in some other pressure unit, when you throw it into the ice table, it needs to be in atmospheres. So that is really important. Again, sometimes people are given problems where they have pressures again in different units and they want their pressures in different units and they go, oh, well, I don't have to change it, but you do. You have to change it, put it into the ice table, and then solve for it. In my made up example on the previous one, could I calculate Q? Let's take a look at that one I had up there. Could I calculate Q in this problem based on what was given to me? I could not because I have no information about C, right? So it's the situation where you could not calculate Q. Let's say I did, or was given in this case, an initial concentration of C. We'll just call it 4 as well. So this would change this to 4, right? Obviously, this would then be 4 plus 2x and so forth. Could I calculate Q now? I could. And should I calculate Q, or does it matter? I'm assuming if I ask the question, it probably matters, right? So you should calculate Q. Now, what would Q affect if you had the question of, are you at equilibrium? My guess is the answer will be no, you're not at equilibrium. Otherwise, it's not much of a problem to actually do. But what happens if I calculate Q and it's not at equilibrium? It tells me to reach equilibrium, I need to make more reactants. What does it change? Which way is this reaction going in that case? Forward direction or reverse direction if I need to make more reactants? It is the reverse direction, right? So if I calculate Q and it told me I need to make more reactants, that means that this guy is heading in the reverse direction. Out of the I, C, and E, what would be the biggest effect on that then? If I'm going in the reverse direction, the amount of reactants, are they getting larger or smaller? They are actually getting larger, which means they actually should be pluses instead of minuses, right? And my products would actually be getting smaller, which means they should be minuses instead of pluses. So this is the second place where you could have to calculate Q, is a problem where you have a situation like this where you're given the concentrations of everybody. You have to do an ice table. It's a really good idea to calculate Q just in case you're in that weird situation where it's actually going in the opposite direction, right? And you would have to adjust your ice table accordingly. I will say the good news is probably 95, 97, maybe 98% of the time, you could almost go on autopilot that is minuses on the left and pluses on the right, but there could be an occasion where it's actually going the other direction. So you do want to keep that in the back of your head. And that is where you would want to use Q in a situation like that to verify, that it is going in the direction you think. So if we calculated Q in this case, and it told us we had to make more products, our table is good, right? Because we're going in that direction, right? We have minuses on the correct side and pluses on the correct side. So outside of a straight up Q problem like we talked about, that would be definitely the second place where you might need to calculate Q if you have enough information. Clearly, if you don't have enough information, You can't calculate Q, and you could assume that you have no products and it's zero and it's heading towards the product side. Any questions on that there? All right, well, there's that example. I feel like we'll hold off and we'll just do a whole day on Thursday of ice table bonanza. Yeah. All right. Any